Um, okay, I'll start off. Good evening, everyone. My name is Rahul Pothraju. I am from the Computer Science Department at Purdue. So, my advisor is Professor Christina Nitrotaru, and I've seen a couple of you, and I've taken a couple of courses with you guys, in fact. So, don't hold anything against me. If you have any questions, just stop me at any time and ask me. Feel free to ask me any questions, in fact. So, of course, again, my name is Rahul, and I put up this slide so that I will not forget to explain what I'm doing, in fact, because I work in a bunch of different areas, in fact. So, I have two core research areas. One is smartphone security itself, both from a client side and a server side perspective, looking at both mobile devices as well as security of Android markets themselves, like, for smartphone markets themselves. The other one is data center reliability, which I do in collaboration with Microsoft Research Redmond. There I study more about the statistical properties of failures regarding, like devices, network devices. How often do they fail? Do they have any patterns, etc. In fact, and I have some few. Like I started off with internet measurements as my core research area. I have a master's from Northwestern University before coming to Purdue to join my PhD program, and I also work in natural language processing whenever time permits. In fact, one of my hobbies is basically combining different areas together. So I do cross-domain research a lot. So today, I will hopefully try to convince you that plagiarism, which is something that is extremely scary in the university setting, is also scary both in the like in an industrial setting. In fact, for instance, smartphone app markets. So my talk today will focus mostly on what is the extent of plagiarism inside smartphone app markets, and what can we do about it. In fact, what is the main motivation behind doing something like this on smartphone application markets, in fact. So before I dive into the actual problem itself, I'll give you a bit of background. So I know that my colleague was here last week giving some talk, I worked in the same project too, in fact. So I tried preparing the slides in a non-overlapping fashion. So, but if you still have any questions, feel free to stop me at any point and ask me more. So there are currently three market leaders in smartphone area, in fact. So you have Apple, you have Google, and you have Microsoft, in fact. Of course, there are the other two are like Nokia and BlackBerry. No offense to them, but they're like tiny players in this whole market, in fact. But the fundamental difference, if you take these three markets, is that Apple and Microsoft, well, like one big thing is that they curate applications. So you as a developer cannot just go upload an application and publish it into the market. So once you upload something into the market, there are these test engineers who actually run these applications through static analysis or sometimes even dynamic analysis and make sure that your information is not getting leaked out to any third-party agencies, in fact. These markets themselves are actually called closed markets, in fact, because they require an additional step of curation, and curation usually takes any time between like 7 days to sometimes. Apple is very notorious for keeping your application on hold for months together, in fact, sometimes. Of course, there's a joke that goes on that if Apple does not like your application, it will always put it in the queue for approval, in fact. And there is this third type of markets, which the second type of markets, which are called the open markets, in fact. The reason these are called open markets is because any random guy, so for instance, I can go and develop something, put up some kind of a hello world application and upload it into the market, and it just gets published instantaneously, in fact. So it does not go through any kind of a verification process or anything like that. So Google decided to create an open market. There are many reasons for doing that. One is capturing developer attention. So if like people who are very familiar with gaming will know this, in fact. So if you introduce more restrictions into the games, your customer base will actually reduce, in fact. So something like that in the context of smartphone markets is that the less limitations you have on developers, the more willing they would be to actually develop applications for the smartphones themselves, in fact. So that being the underlying idea, in fact, Google came out with this Android thing. Android is a Linux-based operating system. The rumor is that there are about 1.3 million new devices being activated every single day, and they have something parallel called the Android market, which the devices themselves talk to, in fact. And this market supposedly has more than 700,000 applications as of October 2012, but I'm estimating the number to be close to 1 million now, in fact. But I don't have any empirical proof for that. So having said that, I have a very complex diagram here, but it's not really as complex as it seems, in fact. So on the left here, you basically see the developer. So that the developer prepares 5 different aspects of development, in fact. So one is called the manifest file, which is at the top. The manifest file is nothing but an XML declaration of what your application is actually doing, what permissions it's requesting, and what are its capabilities. Can it talk to other applications, or can other applications actually start talking to it, in fact? And they have these resources and assets. So resources are basically image files or sound files, in fact, audio files, which your application could leverage. And asset files are usually string mappings. So if you want to do localization, so you want to develop your application for both English audience and Chinese audience, then you do asset manipulations, where you basically map different strings to different languages. In fact, that's what happens. And you have source code and libraries. Source code is essentially Java source code that developers write. So what really happens is the first 3 blocks are passed through something called as an AAPT, which is a packaging application provided by Google itself. What it does is it provides something called as an R file. An R file is something like, if you put a bunch of files into a directory, in order to actually access them, previously what you had to do is you had to open them manually inside Java, like network path, open this particular file and everything. So what Google does at this stage is it creates an R file, which is a constants file. So if you put something like Angry Birds dot, let's say, JPEG file inside your directory, you can just access it saying r.images.angrybirds in your code itself. So once the R file is created, the source code actually rewrites all the like file paths that you have into something like into some constants that the R file produces, and then it's passed through a compiler. The compiler will actually produce like class files. In fact, the class files are then sent through a utility called DX, short for Dexer. What it does is it creates something called as Dalvik bytecode. So if you're familiar with Java programming, you must have heard of Java bytecode too, in fact. So think of Dalvik bytecode. I'll dig deeper into this one. So Dalvik bytecode is it's very similar to Java bytecode, but it's not Java, in fact. So that's the way to understand it, in fact. And what happens later is the bytecode and the package resource file are taken together, concatenated, and then passed through something called as an APK builder. What it does is it combines everything into one single archive, which is ready to be executed on the Dalvik virtual machine, in fact, which reads this kind of code. So, however, the output of this stage is basically an unsigned APK. APK is like you have jar files, you have APK files. That's the basic idea there. So the developer at this stage, what he does is he uses his private key, a cryptographic private key. What he does is he passes that and the unsigned APK through a utility called jar signer and signs it off and generates what is called as a signed APK. So note that only this can be installed on any device. You cannot install an unsigned APK on a mobile device. So that is the core idea you should remember for the rest of the talk, in fact. And once he's finished with the signing process, he can just upload it into the market and it gets in. If you're confused at this stage, for people like me who are like extremely confused with large block diagrams, this is the high level idea. So one of my friends suggested that I present this slide first, but I purposefully did not follow his suggestion. Well, so you have the developer on the left who's basically sending all the Java source files he's writing through a compiler, then through a Dexer to produce like this huge Dex file. So Dex file, the idea of a Dex file is concatenate all individual source files into one large chunk of one large file, in fact. The reason they do this, there are many reasons to do this. Like one is optimization, in fact. So because Java was optimized for the PC, in fact. So Dalvik is optimized mostly for the mobile ecosystem. So they rewrite and they actually use some kind of compression inside and rewrite all this code. Once the Dex files are created, it is merged with all the resource files, as I was saying, and then an APK file is produced, which is then signed, and you have the signed APK. So you're better off with either of the block diagrams. And you should note that like Android uses a Dalvik VM. The fundamental difference between the Dalvik virtual machine and the Java virtual machine is Dalvik is register-based, whereas the Java virtual machine is stack-based. So push-pop operations are supposedly slower, as we learned like in 8086 courses and everything. But like Dalvik is much, much faster. It's easier to actually write Dalvik code. manually even then. So just for comparison, if you have like a 30-line Java by like something like a Java VM code, you can actually write it in like 5 or 6 lines in Dalvik. That's the essential idea there. So one thing at this point is, what does signing an APK mean? Because this forms the fundamental idea of the rest of my talk, in fact. So this is directly taken from the Google developer page, in fact. One thing is, all applications must be signed. So any APK which is unsigned cannot be installed on the mobile device. The other one is, developers sign an application with their private key. And of course, that's not where it ends. So this is the most important part of the developer documentation, which says you can use self-signed certificates to sign your applications, and it does not require a certificate authority, in fact. So how many people here have taken crypto? Okay, so you guys know what I'm talking about. For the people who don't know about it, essentially what this means is, I can take anyone's application, do any kind of a modification, and I can use my own key to sign the application, and no one can figure it out, because there is no central authority to tell me that, hey, the Angry Birds developer has this key. There is no such authority to tell me. So I can pretty much use my own key and sign applications, in fact. So this forms the rest of my talk. So in addition to that, these APK files, if you're curious, all you can do is just do unzip on them. In fact, these are just plain archive files. So this is what I did yesterday evening. I had this Angry Birds Season 2 thing, APK, with me. Doing an unzip will actually produce all these files. So if you're curious about hacking your Android game itself, you can actually do this after hearing my talk, hopefully. So the first set of files is some wave files related to the bird screeches. So how many of you have played Angry Birds? Anyone? Okay, it's a popular game. So the screeching noise that you hear at the beginning of the game is being played by the first 2 files over there. In fact, the bird's boss and everything. And these are the piglet oinks. So you can actually see how the game was constructed itself by the developer. And these are the level files. People have felt free to actually go modify the levels themselves, in fact. And as I was saying, the manifest file that the developer creates is shown in plain text here. So this is an XML file. You can actually go and inspect what is really inside, in fact. And this is the huge file that I was talking about, the classes.dex file. So I was telling you that all the Java source files are concatenated, class files are concatenated into a huge dex file, right? So this is where it's called the classes.dex file. It's a standard naming convention. All applications have this. And finally, you have the shared objects, in fact, shared libraries. For instance, if Angry Birds, in this case, the developer decided to write some native code. So Java is slow. So if you want to do some native floating point operations or matrix multiplications, you're better off writing it in C++, in fact. So that is what this gives you. And finally, you have the signatures. So the signatures are, for each and every single file, you store a SHA-1 hash and make sure that, whenever, these hashes are used to verify that the files have not been tampered with. That's the underlying idea there. So I've told you about this one, and I've told you about this one. So the next common sense actually tells us that, hey, if they are zip files, we can actually unpack them and rebuild them, in fact. That's the underlying idea, right? The first step is still similar. So the developer actually builds all these signed APKs. But if I'm a script kiddie, or if I'm very curious, what I can do is, if I'm an attacker, I can actually decompile the same thing, modify the code in any way that I want, then repackage them and sign them with my own key, and push them back into the market. And that application can actually feel and look like the original, in fact. I don't even have to modify anything. And last year was sensational news everywhere. In fact, this was in fact a very famous set of attacks, in fact. So Symantec discovered some of these attacks where on your left you see the genuine Netflix application. On the right side you see a fake Netflix application. The difference being that the left one, after authentication, it sends you to the Netflix video page. The right one just crashes. And the user mistakenly assumes that, hey, Netflix application is not working on my mobile phone for some reason. I think the Netflix developer screwed up something. That's the assumption there, in fact, and they fall for the trick. However, what they don't realize is the application did not crash. The application exited on purpose, and just before it exited, what it was doing was it was passing on your credentials to some third-party dynamic server, like some server that was logging all your username passwords, in fact. And of course, there is an underground market for all these accounts, so you see where I'm going with this. And not just that. And If we think that, oh, only black hats do this, even gray hats actually do this sometimes. They used it for vigilantism, where the left side application is a simulated dog fight application. So people were encouraged to actually make dogs fight in a simulated fashion. So some guy got angry with this one. He changed beta to PETA, which is like the animal society. In fact, he changed the application so that anytime he simulates a dog fight, a message gets posted to the user's Twitter account saying this one. I don't even want to read that, so you guys feel free to read that. So yeah, and that's it. From then onwards, like there were a whole flurry of these things. So Angry Birds was not left alone, because Angry Birds was a very popular application. So Angry Birds season came out, like Seasons Free came out, except that this time it wasn't Rovio who developed this one. It's a different developer, in fact. Rovio is the original guy who developed Angry Birds. So this started creeping up on the Android market, very frequently, and the response time was maybe 2 or 3 days. But by then, I'll show you by the end of the presentation, like some shocking numbers probably. And finally, there was a very famous Home22 virus. I don't know if I pronounced it right, but so what that it's a malware. In fact, it's not a virus. Sorry, I take that back. So what it does is basically it took all these legitimate titles. For instance, YXPlayer is a video player, in fact. So it took all of them, created counter malwares, in fact, malware counterparts. What it did was it started sending SMSs to private numbers. So do you know how this works? Like essentially, if someone uses your phone to send SMSs, you get charged and they get paid a percentage of that, a cut of that money, in fact. So if you look at this one, they have crazy number of downloads. These malware, like, because people took some time in removing the malware, in fact. So why does this happen, in fact? So that's one thing we'll look into in this talk. There's, at this point, the question comes up, so what have everyone been doing? Like the antivirus guys, probably researchers, security researchers and all. So there is related work. I'm not saying there is no related work, but mostly protection from the client side. People started making antivirus softwares and anti-malware for the Android platform itself. And there came this very famous paper in OSDI 2010. It's called Taint Droid, and I'm sure some of you must have heard that presentation too. It detects information leakage inside mobile phones by a custom operating system. And there has been some work on enriching access control itself. And Google themselves actually came out and said, hey, why not we introduce something? And they introduced something called Bouncer sometime back in January 2012. What it does is it scans all applications on the market side, and then if it finds something to be a malware, a potential malware, it just removes them automatically, in fact. But of course, there is no written documentation of how Google Bouncer works, so there's no way we can analyze it. Some people have tried reverse engineering it, and some people also showed ways in which you can bypass Google Bouncer, so that should tell you something. And there is some work on detecting repackaged applications. So I call them cloned applications or plagiarized applications. People call them using different names, in fact. One of the catchy names was repackaged applications. The first two papers came out from North Carolina's security group. And the third one is mine, in fact, which is what I'm going to discuss today, in fact. But, feel free to, I put up links for all these in the presentation too. So I just finished the background and motivation so far. I'll be talking a little bit about attackers' perspective, the defense perspective, and talk about some evaluation and conclusions of our analysis. So it's not just words. We did this, in fact. So the underlying idea came last year. So where I have a colleague named Andy, in fact. He came one day to me and said, hey, I learned Android programming. I did this nice game, Find a Path. It's basically a graph untangling game. So the goal of that is you're given a graph with overlapping edges, and you're supposed to just untangle the graph so that no edges overlap with each other. So he did this game overnight, and he posted it on the Android market, and he was like, hey, I have about 500 downloads so far. And I was like, oh, that's very cool. And then I went back to my desk, downloaded his application. His was Innovative Creations. That was the company he had, and I changed Innovative Creations to Reflective Creations. uploaded the same application, and I was like, oh, it's such a coincidence that both of us did the same application. And he was like, what are you talking about? And he went to the search engine and tried searching on it, and this is what he found: find a path and find the path with the same icon. And he was like, how did this happen? So of course, the attacker can actually use something very similar, where he uploads the fake application or the plagiarized application, and the user falls for the trick, in fact. So whenever he searches for something that sounds like the original name, he's actually given both of these things. So you should know that Google does not use PageRank. It's hard to use PageRank on Android markets because there are no links anywhere. So, and the whole process took me less than 1 hour and costed me about $25 because I need to get a developer account in the first place. So this brings us to the question, why do attackers even do this, in fact? One of the primary reasons is that you should note that Android market is a centralized market. Unlike PC-based software markets, where developers send users to their own web pages and ask them to actually download something, Android market is slightly different, where every user, no matter what phone he has, he actually goes to the central location and then downloads the application, in fact. Which means an attacker who's successful in executing his attack will be able to reach a large number of users in one go. That's the fundamental idea behind centralized market-based attacks. And the other thing is, these centralized markets imply that there are dashboards. If you've ever seen, if you ever felt bored and started browsing Android market, you will see these top K lists, in fact, which actually show you what are the trending applications or what are the hot new applications that came into the market. So these are some some new lists and everything. So whenever you upload an application into the market, you get a small spot on the top 10 positions, at least for a brief moment. And that is your moment of glory, in fact. Because if a lot of people are looking at that list at that time, you'll end up reaching a large number of customers, in fact. So what we did was we just did some basic analysis where we took about 150,000 applications on the Android market itself, the meta information pertaining to that. What that means is we had what is the name of the application, what is the rating, what are the categories, what are the permissions that it requests, and everything. We did some simple analysis, which is so if you assume a paranoid attacker, in fact, so who's like, okay, you know what, I will just take the application and just upload it in my name without changing any permissions. Because there are informal studies actually in user interactions which show that the lesser the number of permissions, the more user base you will have. People are interested towards installing applications which request low number of permissions, in fact, which is also common sense, in fact. So if an attacker wants to actually upload any kind of an application without changing the permissions, I mean, you have lots of things to just attack in plain sight, in fact. You don't even have to go modify anything. So you have privacy-based permissions, you have monetary-based permissions, and this is the deadliest of all, which is install packages. What it gives you is the power to install other packages, in fact, through the application. So these many number of applications, which is about close to 29%. So what that means is a script kiddie who has no knowledge or who's very scared of being discovered can actually go and attack 29% of the applications on the Android market at this moment, in fact. So that's what it means. And later analysis, what we figured out was if I were an attacker, it would make sense for me to actually target mostly popular categories, even though I risk a higher detection rate there. Because applications from popular categories means that more people are monitoring them. But at the same time, you should remember that if a large number of people look at that application, they will end up downloading it, in fact, which means you'll reach a higher customer base. And we found the most vulnerable category of all is basically arcade and actions, because the rate at which an application gets downloaded the moment it gets onto the market is very high, the highest, in fact, in arcade and action. And one other thing is you could actually release on a weekend. This is common sense, but we found some empirical proof saying that if you release on a weekend, you will end up reaching a larger number of users, and your attack would be more successful. And one other thing I found in the parallel study was you could also release it on a Monday morning. I have no idea why you can do that, but it is more likely that people are just getting out of the break mood, they go to the work and then they start browsing on their phone or something. Maybe that's the reason. So having said that, I'll present some, like this is, of course, this is not an exhaustive list of defenses against such an attack, in fact. This is one such defense. What do we want to do? So, okay, all this drama is happening, in fact. So there is so much going on, in fact. What do we want to do? So if you still remember this picture, so what we want to do at this point is when an attacker actually tries to upload an application to the market, we want to give back a message to him saying that, sorry, we found a duplicate to your application and you cannot upload this. You may have to contact the original developer, or you may have to go for a manual curation. Because think about it, if you have to manually curate every single application, you will need a lot of test engineers, in fact, which Google is very hesitant to put on. That is where automatic solutions like this actually come in handy, in fact. The high-level overview of any such idea, what are we trying to do? This is a variant of anomaly detection, in fact. So, if we have a bunch of applications and we're trying to look at suspect applications, how do we say that, okay, like if there is some kind of, anomalous behavior that the application actually has, how do we basically say that? And the higher-level idea of any such mechanism, not just this one, is you take all original applications or original data, then you fingerprint them, in fact. You fingerprint them and basically store the feature vectors somewhere inside maybe a database or some kind of a data structure. And whenever you get a suspect application or a suspect data point to examine, what you do is you pass it through the same procedure, build a fingerprint, then you compare it in some way. The comparison itself is dependent on the algorithm that is being used, in fact. And usually the comparison is threshold based, essentially if the distance, as they call it. So these are all high dimensional spaces. The feature vectors themselves project the application or the data point into a high dimensional space. So if 2 points fall onto the same, same high dimensional data point, it means that both are very similar, in fact, or we could even say they're same. And that kind of a distance calculation is what most of anomaly detection is. So if the distance is less than some delta, or some kind of a threshold, that's what we're interested in. So now that begs the question, how do we extract a feature vector to begin with? So in the next couple of slides, I will also show you how to reverse engineer if you don't already know, in fact, which is something cool. You could go and try it back home, but don't name me anywhere. So you take an Android binary, and what you have to do is basically, the essential idea is there are two stages. One is reverse engineer to actually get some kind of a code, some readable code, in fact. And the second step is to fingerprint that code. That's it. The block diagram itself has 4 stages, but if you think about it intuitively, what I'm trying to do, it's taking a binary, producing some code that I can read, and then I'm doing some fingerprinting, in fact, so that I can store these fingerprints somewhere for future comparison. That's the right way of understanding it. Now, reverse engineering, well, there are multiple ways of doing reverse engineering. If you really are a masochist and you want to torture yourself, the hard way is to actually build your own reverse engineering, which is what I did last year because there were no tools available to do this. So in order to go that route, essentially, you will obviously learn more if you're doing it yourself. So I did learn a lot in this process. The first thing is to discover that, or maybe rediscover that Dalvik, the virtual machine itself, was inspired from what is called as a Jasmine syntax. So Jasmine syntax is opcode mappings. So anytime you actually write, the code and everything we learned, right, it gets converted into assembly code and everything. So Jasmine syntax actually gives such opcode mappings to convert source code into like assembly code, in fact, or the bytecode. And learn the following fact, that Android is not Java, but it still has traces of Java inside it. And it follows a bytecode format. And anything that follows a bytecode format, it means that opcode mapping should exist. I mean, if the machine has to understand, there should be some kind of mappings available. And if the mappings are available, we can get access to them too, in fact. And you should just accept that as of today, to the best of my knowledge, there is no way you can get back the original source code from the bytecode itself, because the compilation process is a bit lossy due to compression and everything. And then the final step is you code a decompiler, in fact, by leveraging these opcode mappings. The one that I did was about 1,500 lines of Python code. That's small enough. Of course, the easy way for you, if you want to try it out now, is you have a bunch of utilities here that I posted. Ddexer is a tool given out by Google itself. It will not give you any source code that you can read, but it will give you assembly code that you can actually go and dive in and read, in fact. The other very popular one is called dex to jar. What it does is something very cool. It produces source code that looks somewhat similar to Java source code, but you cannot compile it back. So you can just read it for inspection. How does the program work? So you cannot modify something and really compile it back. The third one, which is very famous in the hacker community, is called the APK tool. What it lets you do is decompile. You can even modify anything inside it, and then it will let you repackage the application. It will let you recompile the application. That's what I mean by that. So far what we've looked at is basically that reverse engineering thing that I've been talking about, right? Reverse engineering is just half the story, in fact. It gives us some code that we can start reading. But there is still the next step of fingerprinting. Fingerprinting is the process where a common set of people, let's say, we agree on certain features that we can use to compare different data points, in fact. So in this case, if I give you, so this is how the reverse engineered code actually looks like, in fact. So this is the Jasmine syntax, to be very specific. What we're trying to do is, we're trying to look at unique fingerprints inside the code that will let us compare different programs. So what we're trying to do here is, let's say, I could randomly pick certain things. There is a whole area about feature selection, in fact. How do you properly select features in machine learning? But I won't go into detail in that aspect. But what I could do is, hey, I will take the method name or maybe the function name that is being called as different features. So if two applications are actually calling the same function, or maybe have the same function name, I could mark them as being similar. That's the simplest way of putting it, in fact, as to what I'm doing here. So the idea there is, the columns will represent different features that I'm actually using, and the output of such a feature mapping, essentially, like you take the program, you build a feature vector, is just, it could be binary, or it could be like, it could be a decimal number too, in fact. So there we go. There we have like the high level idea there. The idea is to first reverse engineer to get some kind of an intermediate format. Of course, this is a completely optional step. You could just directly operate on the bytecode, provided you know what you're doing there. But because we are humans, we like reading English, like some language that we know. I think it's better to just get to an intermediate format. The second one is build abstract syntax trees. So I'll get to what these are in a minute. How many of you know what ASTs are? One. Okay, I'll get to that. Okay. The third one is actually fingerprint these ASTs. So the core of the idea lies in the second step. How do we build abstract syntax trees that can represent the given code, in fact? So I was telling you, right, this is how the reverse engineered code looks like, in fact. If you have reverse engineered code like this, one of the first things that would be useful in doing is parameterizing it, so that you don't confuse variable names, like different variable names and everything. So what I mean by that is, you could just substitute I or whatever the parameters are there inside using standard parameters. In fact, for instance, I don't care if the function is actually being sent an integer or a string. All I need to know is the signature of the function. Maybe I could do better using integer or string, but I decided to go just with the argument, in fact. So this is purely based on the anomaly detection engine itself. You could decide to make it as strong as you want, or you could trade off certain features, in fact. So what you do is, you take the integer, you map it onto something called as an argument, and you do the same thing like everywhere, in fact. So here v2 is basically a local variable that is being used, and this is a parameter that keeps changing. So what the output of the first step is, take the code and then parameterize it, and so that you will get something like an abstract representation. The advantage of abstract representation is that you will be able to compare, even if the attacker modifies a small thing over there, our mapping is kind of immune to that. That's the general idea there, in fact. And once you have that, how you build this? So abstract syntax trees are essentially like, if you've taken the compiler class, what they do is basically, they are a representation for the compiler, in fact, on what is the order of compilation or something of that order. Here, this is the idea, the high level idea itself is an abstract syntax tree, but this is actually very simple on how to construct this one. So what this tree is actually saying is that this is a method which actually takes in one argument. From here, this is one argument, and it calls or invokes two different types of functions. One is a direct function, one is a virtual function. And there are other kinds of functions too, like static functions. So if it calls a static function, there will be a third node here saying that this is a static function. And each of these direct, we record the signatures of those things too, in fact. Local and param, in fact. And that's pretty much it. So that's the trick here. You basically build this abstract syntax tree, and you will move on to one final stage where we ask the question, how do you, okay, now this is a tree. Now how do we compare two trees, essentially? So if you've taken graph theory, like essentially one known problem there is graph isomorphism. It's hard to do that, computationally expensive. So what we instead do is we start searching for alternate ways of actually doing this, in fact, right? So the question here is, how do you map this abstract syntax tree into a feature vector that you can actually store somewhere inside a database? So that process is actually called structural fingerprint extraction. This is a technique that is sort of becoming famous in software engineering in an area called clone detection. If you haven't already observed, what I'm trying to do here is somewhat very similar to clone detection, where I want to try and figure out if two pieces of, or two fragments of code are actually very similar in nature, in fact, right? So the paper actually, like my paper actually discusses this in great detail, but the high level idea here is, given a tree like this, I want to capture every single feature inside the tree. So by feature, what I mean is all horizontal features and all local, like all vertical features, in fact. Now, how do we basically capture that? Permutations and combinations. You basically take method, and then you basically start enumerating every single combination out there. And because I know what all kinds of nodes are actually possible in the tree, this is bounded. The length of the feature vector itself is bounded, and I made sure that the length is maybe 20 or 22, in fact. So the idea here is, okay, so method, how many nodes did it actually see which have method? It's one, and so on. Like method virtual is just one. So that is what it is actually recording in the last column of this table, in fact. And finally, building the feature vector itself is these numbers. That's pretty much it. So that's the magic trick there. So you take the abstract syntax tree and then you map it into a feature vector. Now once you have the feature vectors, you can start doing wonderful things. So the implementation itself, this wasn't as complicated as the reverse engineering thing itself, because that required opcode mappings and all. But this one, given a program like this, to convert to this one, it was about 400 lines of Python code, which is kind of good, maintainable size, I guess. So now that we have all these feature vectors, I will now present two different kinds of algorithms, in fact. What they do is, they'll actually tell you if two given applications are very similar. That's all they will do, and there are multiple ways of doing it. So the first is called the distance based. The underlying idea there being that is the distance, so we are asking that fundamental question over there, that is the distance of a suspect program sufficiently far away from its neighbors, in fact. So if you consider that this is a high dimensional space, let's say we projected that into a 2D space, in fact, and we look at all these Android applications, or these data points could be anything, in fact. In my case, these are like Android applications, in fact. So given a suspect application, all we're trying to do is it placed sufficiently far away from the data points? The second one is called coverage-based algorithms, where I'm trying to ask the question, what amount of the benign program is being covered by the suspect program? So the underlying idea there is that, let's say I am the benign Angry Birds program and I have 100 functions. If you're the malicious guy, you don't have to remove any functions, you just need to add some malicious functions to it, right? So if you take the intersection of these functions and you find that there is a very high coverage there, it means that there's something fishy over there. So the first of that type itself is called AST distance, where what we do is, in the preparation stage, we take each and every Android binary, we build the feature vector for all individual methods. So this is after all reverse engineering, in fact. Once we get all the reverse engineered byte code and everything, we start building feature vectors for each and every individual method, in fact. And what we do is, we just sum up. I mean, we have different techniques in the paper, but I'm presenting something that is simpler to explain. So you take all the multidimensional vectors, you sum them up. The resulting vector is the fingerprint for that program. In fact, that's how we look at it. And yeah, so the output is basically a feature vector for the entire program. The second step is checking. So given any kind of a suspect application X, we do a similar process, get the feature vector for the entire thing, and then look at the distance. How far is the suspect program from its nearest neighbors, in fact. And if it's less than a threshold T, like I was actually saying at the beginning of my talk, it's essentially there's something fishy about it. That's the way you do it. And AST coverage, like I was saying, so let's say you have a benign application with 3 nice methods like that it is using to run the application. A suspect application could add additional methods or change, like modify some of the existing methods too. That is definitely a possibility. So in the paper we explain why the fingerprinting technique is actually robust to minor modifications. Of course, if you end up using like level 3 obfuscations and all, this won't work. But again, I'll come to the limitations in the end. So the idea there is, now this is the suspect program, this is the benign program. We're actually looking to see how many methods actually match in the suspect program. And in this case, we do this small computation, and it actually says that in this particular case, all the 3 methods matched with the suspect case, so this application could have been potentially plagiarized. That's the overall idea there. So some of the goals of like evaluation, a good evaluation methodology would be to ask 2 questions. One is it accurate, in fact? Because I don't want this detection algorithm to go and implicate someone innocent, saying that, hey, you know what, you plagiarized my application, in fact. So that is goal number 1. The other thing is actually to see whether it performs well on obfuscation, in fact. So if I end up using obfuscation, will it still work, or will it just break with very simple obfuscations? And the third one is it able to detect real world malware, which came out, let's say, because now we have the ground truth. We know what came out last year, right? So can we actually go and detect those things? That's what we want to see. And the second question, which is also very important for scalability reasons, is it fast enough? Can the detection engine just work? Does it take seconds to detect something? Does it take hours to detect something? So for this, what we did was we basically obtained about 7,600 odd Android binaries. This number is small. My current data set is close to 100,000. So yeah, this is at the time of writing the paper. So these are executable APK files, which are binaries. You can actually install them and play around with them, in fact. And this accounts to about 320 GB. So the idea there is to take each and every binary, reverse engineer, get the code, build the feature vectors, then try to do intra-application comparison and see if any applications are there which have been plagiarized already, in fact. So that's the underlying idea. So how do we estimate accuracy? There are 2 ways in which we do this. One is we create a virtual Android market because we don't have access to the original Android market, right? So we create one web server which we represent as a virtual market. It contains 7,600 apps. Now if an attacker actually uploads a plagiarized application, will it detect it? That's the first question we want to ask. The second thing is, if you remember, we don't want to implicate any innocent applications. So what we do is we construct an alternate virtual market where what we do is we take off all victimized applications. What I mean by that is, like, if the attacker is uploading a fresh new application, it should not be marked as a plagiarized application. That's what we're checking in the second stage, in fact. So that is to answer this question, whether it will implicate other innocent applications. That's what we want to look at. So what we did here is, this list we found out automatically using nearest neighbors, in fact. So what we did was we did an intra-market comparison. So we have all these applications and all of these. So we do this n-squared comparisons and actually try to get the closest neighbors to each application. So this application had a crazy low distance when compared to the Flash player thing there. And what we did was we manually went and inspected everything. The entire code is the same thing, except the developer name was changed and a little bit of some I guess communicating with a third-party server, like that kind of a code, like maybe 6 or 7 lines was added essentially to it. And it was the same in every case. What we found out was, I mean, these are instances of malware that were popular last year, in fact. So in almost all cases, we had like 100% detection accuracy. There's nothing fancy going on. If you look at the algorithms, it's common sense. The attacker, what he's doing is he's trying to replicate developer names and everything, and all we're trying to do there is figure out a really extremely fast way of comparing applications together. In fact, that's the way to look at it. Of course, here there was something funny happening. So like in this particular case, we did, like the distance of the plagiarized application was a little bit far off from the original, not by a lot, but a little bit. So what this guy was doing was he went and tampered around with the existing code for some reason, which we could not figure out why. Maybe he changed the wallpaper or something inside it. I really don't know what happened there. And the second question we wanted to ask was, will it actually implicate any benign applications, right? So what we did for that is we removed all these legitimate titles from our market, and then we tried inserting these titles inside. So ideally speaking, it should say that there are no other applications that are similar or close to this particular application that you're putting in, right? So these are the numbers for the minimum distance, in fact. So closer to 1 means it's very similar. Closer to 0 means that I could not find any application that is very close to whatever you're inserting, in fact. That's the essential idea. And here's where the fun begins, in fact. So it wasn't just pure numbers. So we found something like this, where the one that you saw on the one that you see on left is real Angry Birds. The one that you see on right is fake Angry Birds, in fact. And it looks very, very similar and behaves like the original Angry Birds too, in fact. And if you look at the numbers, I purposefully removed the developer name. I don't want to get into any lawsuits here, but Rovio Games rating was 4.7, 43K people rated it. It's greater than 250,000 at that time. Look at this guy. The rating is 3.32, greater than 250,000. And there were some jokes being cracked in the reviews saying that you guys should really learn from Angry Birds. They're doing it in a really good way. But why is your game so laggy, in fact? Why is it not functioning well? So what that actually indicates is people didn't even discover that this application was kind of plagiarized from the original one. So some of the things that are interesting to systems people, in fact, is we did not use any fancy processor here. We used an 8 gig machine with a quad core. And this is the trick, by the way. So for nearest neighbor queries, like these feature vectors, ideally what you would do is you would actually do an n-squared comparison. So given a feature vector and you have a list of feature vectors to compare, what you would do is you would actually compare it like in normal Euclidean distance or something like that, right? So here what we do is instead think of this as an equivalent to indexing in databases, in fact. So any query on a non-indexed database would take probably, it might sometimes take a minute or two, right? Once you index it, it just catches something like in an instant, in fact. So this is somewhat similar to that. It maps all the feature vectors to a data structure called a KD tree, and it performs fastest, fast nearest neighbor queries on that. So to give you a perception of which one takes the maximum time, these are like numbers on an average, in fact. So decompiling takes about 6.3 seconds on an average. Feature vector construction is the most expensive. It takes about 12 seconds, and that's the one slowing down everything. We're looking to parallelize that, but we haven't gotten down there yet. And fetching the k nearest neighbors, k is like variable, in fact. I can say, get me the 5 closest applications to whatever I'm looking at, in fact. And I could be very well off. And then the final output, preparing the UI or saying that, hey, you know what, this is the one that's like 0.1 seconds for. So that's, in total, it's less than 20 seconds, and that's the kind of selling point for the idea. And some other interesting points about the building the data structure itself, because KD tree is the most expensive one. Like once you build it, you can actually pretty much do a lot of cool things with it. So for building it itself, it takes under 2 hours. So what we did was we evaluated it on hypothetical markets. So what we did was we take like the Android market, create, replicate applications inside it 10 times or maybe 1,000 times in fact. So the size of these markets are close to about 2 million or 3 million. We want to be futuristic, right, essentially. So that's why we're trying to project numbers and see. And this gives comparison of the different algorithms that we gave in the paper, in fact. So I did not really discuss symbol coverage. That's given in the paper, but the AST distance is very trivial. In fact, it's the fastest, but we show in the paper that it is it is bound to some inaccuracies. In fact, so it has some false positives. But AST coverage is much better, and there's a trade-off that it's a little bit slower actually. And once you build the KD tree itself, this one is for scanning for plagiarized applications. So what this measures is, given an application, how long does it take for me to reverse engineer the application, build the feature vector, and compare it with my database, in fact, of feature vectors. That's what it is showing. And in most of the cases, symbol coverage is again gone, but AST coverage actually takes the second maximum amount of time, because it has to go through each and every feature vector. Whereas in AST distance, it's basically comparing 2 feature vectors. AST coverage is dependent on the number of methods that an application has. So at this point, there are a few things to clarify, in fact. So this solution works. There's nothing wrong with it, but there are some limitations with it. So if you closely follow antivirus vendors and all, it's an arms race. So the antivirus guy comes up with an update that is super nice and everything. The virus writer comes up with a much more sophisticated one and then says, hey, I can break your antivirus, in fact. So this is somewhat similar to that, where attackers can actually resort to much more sophisticated attacks, where they can do semantic tampering. So what semantic tampering means is, you have this huge method. You basically, all you do is you split it up into smaller methods, in fact. Once you start doing that, of course, it's difficult to do it. That's the reason most attackers don't even bother about it. But if you're a sophisticated attacker, then this method will not work, or you need to make some modifications to it. And if the attacker is at the level of actually going and tampering with the underlying virtual machine itself, then that's pretty much game over there. And finally, we have visual tampering. So I was showing you the Angry Birds example, right? So the 2 applications don't really look identical. What they did was they introduced some kind of randomization. So because every image that is inside a game has to have some coordinates. So you can always go and tamper with the coordinates and change it. So the method still works with visual tampering, but you can have alternate methods that are much more robust, in fact, to detecting visual tampering inside applications. And from a defender's perspective, there are other ways in which you can solve it. One obvious way is to introduce some kind of curation. So what we tried proposing is, put the system there. If it actually says that there is an identical application somewhere, then go and do the manual curation. You don't have to hire people to do the manual curation, in fact. The second one is, look at all the obfuscation attempts that are being made and build better static analysis tools, in fact, because Google is currently looking at dynamic analysis, and there are tons of problems with dynamic analysis. For instance, take a banking application. You need a username and a password to get in. Do you guys know what dynamic analysis is? So one line overview is, you take an application, execute it inside a controlled environment, then start monitoring it, in fact. If it's leaking out some information, you will have some method to actually capture that. And then you can say that, hey, okay, there's something wrong with this guy. The problem with such approach is that it requires user input. So dynamic analysis, automating dynamic analysis is a very hot, active area of research, in fact. So it's not yet there in production. And having said that, what I've shown you is what is the attacker perspective of actually executing such attacks. And this is not an attack that will go away. It's an arms race. People will keep doing this. Google will try to take off these applications everywhere and all. And we did propose some defenses to such attacks, which are not foolproof, but they are fair enough to actually stop intermediate level hackers, in fact. And finally, this is not a panacea, but a first line of defense. More sophisticated work is coming up now, in fact, on addressing obfuscation attempts too, in applications, in fact. And I put in a couple of references if you're interested in actually looking at reverse engineering in more detail, in fact, or if you have any questions, just feel free to email me. And I would end it there. If you have any questions, I'd be glad to take them. Okay, so I'll assume that there are no more questions. I was sitting in your place a couple of months back, so it's okay. Alrighty, guys. Thank you very much for your time.